So the next thing we're going to do is talk about volumes of revolution. And we've discussed how to find the area of a plane region bounded by two curves. So that's what we've been doing. And now what we're going to do is we're going to try to take that and then rotate them essentially to make them three-dimensional. So we're going to find a three-dimensional solid from a two-dimensional object and then rotating around the x or the y axis. So we're going to discuss how to do that with discs and washers and then with cylindrical shells. All right. So basically what we're doing is we're going to let S be a solid that's bounded by two parallel planes perpendicular to the x-axis. X equals A and x equals B. And then we say if for each x in A and B, the cross-sectional area of S perpendicular to the x-axis is A of x, then the solid revolution is this. Now you might think, what in the world are you talking about? But essentially what we're saying is, if we just draw a very quick sketch, is that if I have some area here, let's say, that I'm bounding, so this is my area x, these are my perpendicular planes. What I'm going to do is I'm going to revolve that around the x-axis. So I'm essentially going to trace it all the way around the x-axis. And as I do that, what I do is I actually end up creating a three-dimensional shape. Okay? And that three-dimensional shape now looks like a sort of cone sort of thing, but that's what it looks like, and I'm not an artist. But the idea is that you take the area and you rotate it around the x-axis and you create a three-dimensional shape. Okay? That's the idea. So to do that, we use this method, and what we do is we figure out what the solid is by revolving a plane region about a line that lies in the same plane as the region. In other words, we're going to stick to the x-axis. So to find the volume of solid revolution, we have to take the integral of a cross section of the solid. Okay, and as you do that, if you think about what that looks like, it's essentially a circle. So in other words, if you think about it this way, and I'm going to redraw this again. And here's my region, right? And it's a little bit different than the last one, but let's say that's my region. As I take this point and I rotate it around the x-axis, I'm going to trace out a circle, okay? Just from that point. Then if I take this point, I'm going to trace out another circle, a different circle, right, as I go around. And as I do that with all of the circles from here, from each of these points, from here all the way up to there, I'm creating a series of circles, okay? The area of which is this. It's pi r squared, where r is the radius f of x, because you think about it, you're going this distance here, and then you're going the exact same distance down here. So the idea is we're taking each point in our area, each of these points, and we're rotating them around the x-axis, and they're creating a whole bunch of circles, okay? And those circles combine to make my shape, my volume. That's the idea. Now you might be saying, okay, I think I understand what you're saying, but how do I find all of this stuff, and what do you mean? So let's do an example, and I think it'll become relatively clear. So here's an example. It says find the volume of a solid that's obtained when the region under the curve y equals root x over the interval from 1 to 4 is revolved around the x-axis. So I start by saying, okay, if that's the case, what does y equals root x look like? So this is what it looks like. All right? And we know at 1 it's 1, and at 4 it's 2. So here's my region. This is the region that I'm going to rotate around the x-axis. So all I do is I take the volume formula. It's pi times f of x squared. The boundaries are 1 and 4. The function is root x. Okay? And I square that. So what I end up with is a volume integral from 1 to 4 of root x squared dx. And then I integrate. So root x squared is x. I integrate that and get x squared over 2, and I'm going from 1 to 4. Leaving the pi here, it's still part of my volume, okay? So I get pi times 4 squared over 2 minus pi times 1 squared over 2, and that gives me 16 pi over 2 minus pi over 2, which is 15 pi over 2. So the volume of the shape that I've created is 15 pi over 2. Now, if you have a textbook, it's probably got pictures in the textbook that are a little better. My textbook that we're using in our class, and your textbook, I guess, since we're using the class, if you go to page 470, it has some nice little pictures. And I'll just see if I can show them to you. They're kind of, I don't know how well you can see them, but they're on the bottom of the page right here. And they show you what happens when you revolve certain shapes, certain two-dimensional shapes, around the x-axis, and it creates three-dimensional shapes. So that's the premise. Those are the different shapes. That's the premise, and it's a little bit hard to draw for me because I'm not an artist, and drawing in 3 dimensions is not my forte. But that's the idea in terms of what you're actually doing visually. But then mathematically, what you're doing is just figuring out what the area is that you're revolving, and then when you revolve it, you're plugging it into this volume formula. Okay. So let's do one more example. Let's derive the volume of a sphere of radius r. So to do that, we have to think about what kind of two-dimensional shape is, when we revolve it, going to create a three-dimensional shape. Okay. So as I trace this around, what am I going to use? And it's going to be a semicircle, because if I take a semicircle and I rotate it, the semicircle traces out a full sphere, a ball, basically. All right. So I'm going to go from minus r to r because it says to find the volume of a sphere of radius r. And the equation of this semicircle is going to be, if you think about the equation of a circle, it's x squared plus y squared equals r squared. We've talked about this before. What you're going to do is you're going to say, I need to solve that for y. Y equals what? So we're going to go y squared is r squared minus x squared. So y becomes plus or minus the square root of r squared minus x squared. And what I want is actually the positive one, because I want the one above the x-axis. So I get this. The volume is going to be from minus r to r, because that's where I'm starting and ending. And then of f of x, our f of x is the positive one of these squared. So I square it, and it gives me this, r squared minus x squared. Then I integrate. The integral of r squared is going to be r squared x. The integral of x squared is x cubed over 3. So I get this, and I'm going from minus r to r. Okay. Now I plug in r, and then I plug in minus r, and I get this. I get r cubed, because it's r squared times r, minus r cubed over 3. And then minus r cubed, because this is minus r now, and then minus r cubed over 3. Okay. And if I simplify that, I get r cubed minus r cubed over 3 plus, because it's minus a minus, r cubed, and then plus, but then minus. There's 3 negatives. So 1, 2, 3. So minus r cubed over 3. And I end up with this, 2r cubed minus 2/3 of r cubed, and that gives me 4/3 of r cubed times pi. And that's the volume of the sphere. Okay, so that's where we'll end that video. We'll talk in part 2 about what happens if there's holes in the function. And there's a lot more examples there in your textbook as well on page 471 and so on that will show you how to do that. But that's the premise.